Hello everybody and welcome to the video for section 6.3. Before getting into what this section is about, we should recall what the previous video was about and what chapter 6 is about. Chapter 6 is about solving traveling salesman problems. And remember that these problems, the sort of canonical example of one is a salesman who has to go to several different cities to try to sell his stuff. Now, he can travel those cities however he chooses. He has to start at city A because that's his hometown, but he could visit, city D first and then city E next and city B next and then back to A or whatever, Or he could travel to city D first, then C, then B, then E, then A, whatever. So in general, a traveling salesman problem consists of somebody who has to travel around and a bunch of destinations that he or she has to go to. And furthermore, there are costs associated with movement. So if you're going to travel from city A to city B, there's some cost associated with that. And that cost might be money, or it might be time, or it might be a distance cost, whatever. There's some notion of cost. So that was the notion of a traveling salesman problem that we introduced in the previous video. The next 3 sections are dedicated to solving these problems. So recall that in chapter 5, when we were doing street routing problems, we started the chapter by setting up the kinds of problems we were interested in, and then we spent the rest of the chapter developing solution techniques. And in chapter 5, the solution techniques involved looking at Euler paths and Euler circuits, and either Eulerizing or semi-Eulerizing if necessary. So if somebody handed you a graph, if there was an Euler circuit already there, you could find it using Fleury's algorithm. If there wasn't an Euler circuit already present, you could build one by essentially Eulerizing the graph, by adding in edge duplicates. That's what chapter 5 did. Now in chapter 6, instead of dealing with Euler stuff, we're dealing with Hamilton stuff, and the theory from chapter 5 does not translate. So the next 3 sections that we're going to do will look nothing like the end of chapter 5. To solve traveling salesman problems, you need different techniques. Before getting into the solution technique we're going to talk about for section 6.3, we need some preliminaries. And firstly, we need the idea of a complete graph. So a graph is complete if, given any 2 vertices in the graph, they're connected. So every vertex is adjacent to every other vertex. That's what it means for a graph to be complete. If the graph has n vertices and it's complete, then it's denoted with a k sub n. So let's just look at some pictures here. Look at case 6, for example. There are 6 vertices, and notice that every vertex is adjacent to every other vertex. If I'm at this vertex here, in a single step, I can get to any other vertex. So in K3, the same thing is true. If I'm standing at this top vertex here, I can get from this vertex to either of the other 2 in a single step, and so on. So again, K stands for complete in German, I believe, not in English, obviously, but K for complete, and then the subscript tells you how many vertices there are in the graph. So K5 is the complete graph on 5 vertices. K7 is the complete graph on 7 vertices. There's also a K sub a billion, if you really wanted to draw a billion vertices and have them all be connected. So again, a complete graph is simply a graph in which everybody is adjacent to everybody else. All the vertices are adjacent to all the other vertices. So if I took this triangle here and deleted this edge right here, the graph would no longer be complete because then the bottom left and the top would not be adjacent to each other. So here are a couple of pictures of complete graphs with context filled in. These are 2 graphs from the previous video. This is our traveling salesman starting at city A, and he has to visit the other 4 cities. This graph represents our satellite, and the numbers here represent time costs. So it takes 8.2 years to get from Earth to M. But the thing to take away from these graphs are these are both complete graphs. So in this graph right here, at any vertex, so at Titan, say, right, I can get to any of the other 5 vertices in a single step. Same thing for Earth, for G, for Callisto, for Io, for M, right? all of those vertices are adjacent to everybody else. Notice this graph has the same kind of structure. B is adjacent to C because there's an edge connecting B and C, adjacent to D, adjacent to E, and adjacent to A. Okay, so, and same thing goes for the other vertices too. E is adjacent to everybody, D is adjacent to everybody, etc. For reasons that will become clear later, we need to be able to count the number of Hamilton circuits in a complete graph with n vertices. So without explaining where this comes from, just in the interest of time, let me tell you that the number of Hamilton circuits starting at a particular vertex in the complete graph on n vertices is, take the number of vertices, subtract 1 from it, and then do the factorial symbol. And this symbol is something we introduced back in chapter 14 or 15, or maybe 16, I forget, in the probability and statistics section. So if you forget what it means, you can of course Google it, but also you can reference the previous videos. So here's an example. So here's a complete graph on 5 vertices, and suppose I asked you, how many Hamilton circuits are there in this graph starting at vertex A? Well, the answer is, well, there are 5 vertices in the graph, right? A, B, C, D, E. So the first thing you do is take 5 and subtract 1. You're left with 4, and 4 factorial is 4 times 3 times 2 times 1, which is 24. So in this picture here, there are 24 Hamilton circuits starting at A. Now, why does that matter? Who cares? You know, who cares that there are 24 Hamilton circuits starting at A? The reason we care is that this traveling salesman needs to walk a Hamilton circuit, doesn't he? Because a Hamilton circuit, in more vernacular language, is simply an optimal tour of the cities. So he needs to start at A and end at A and visit each of the other cities exactly once. Okay, doing that is a Hamilton circuit. And now we know there are 24 different ways for him to do that. So if you start listing them, you can go from like A to B, B to C, C to D, D to E, E back to A. That's one Hamilton circuit you could walk. Or you could go A to C, C to B, B to D, D to E, back to A. Or you can go A to D, D to C, C to B, B to E, E back to A. You know, there are all sorts of ways you can do this. And now we know that if you were to list them all, you should have 24 when you are done. So again, the number of possible ways that this traveling salesman can walk the kind of route that he wants to walk is 24. So now let's move on to actually solving a traveling salesman problem. So in this strategy, we will look at 2 strategies, and actually 2 here is a typo. I forgot to modify this particular part of the slide based on an old slide. But anyway, we're only going to look at a single strategy in section 6.3, and it's called the brute force algorithm. So before discussing what it is, suppose I just gave you this graph and I said, look, I insist that you find the cheapest way for this traveling salesman to start at A, end at A, and visit the other 4 cities. You know, I insist that you find me the cheapest possible route for him to do that. Now you must do it, right? So go off and do it and tell me what you did, right? Well, if we were in class, I would of course just ask you, what would you do, right? And in class, the students generally agree that if I insist that you get the cheapest path, the students all generally agree that the way to do that is to simply list all the possible ways he can walk, find what the corresponding costs are, and then pick the cheapest. So for example, we know ahead of time that there are 24 possible routes that he can walk. So we could literally list them all, see what the corresponding costs are, and then choose the cheapest one. That's what the brute force algorithm is. That's what it does. It says, look, you want to solve this problem? Well, you can use an exhaustive search, which literally means we're going to write down everything that could possibly happen, compute all the possible costs, and then see which one is the cheapest. The reason this is called brute force is because it's not terribly smart. Like, there's nothing efficient about it, but it will get you the right answer. I mean, if you literally list everything, all possible paths that this traveling salesman can walk, you list all the paths, compute all the possible costs, and then just look and see which one is cheapest, you will indeed have solved this particular traveling salesman problem. So here's what the algorithm is, the brute force algorithm. What you do first is make a list of all the possible Hamilton circuits of the graph that start where you want to start. So in this case here, we would start at A. Okay, each of these circuits represents a tour of the vertices of the graph, a way of visiting all the vertices. For each tour, you calculate its overall cost. And you do that by adding up the costs of all the edges. And then once you've listed everything, you can literally just choose one that's the cheapest. And usually there's more than one, so you choose one of them randomly. It doesn't matter. So let's solve this exact problem here. So again, I'm the traveling salesman starting at city A. I need to visit B, C, D, and E. I need to visit each of them exactly once, and then I have to return to A. Well, here's what the brute force algorithm looks like. So remember, step one is make a list of all the possible Hamilton circuits of the graph that start at the given start vertex. These two columns here, these outer columns, tour and tour, these are all possible Hamilton circuits that start at A. You can go A, B, C, D, E, A. You can go A, B, C, E, D, A. You can go A, B, D, C, E, A, etc. There are 24 total, and we know there must be 24 because we calculated it already. Now notice that one of the things that's nice about this table, and we haven't finished analyzing it, okay, we're going to spend a little bit more time on this, but notice that this tour here, A, B, C, D, E, A, look at the corresponding entry over here. This is A, E, D, C, B, A. Do you notice that 1 and 13 are mirror images of each other? So A, B, C, D, E, A. Let's go look at what that exactly does. A, B, C, D, E, A. So you literally just walk around this way. Well, A, E, D, C, B, A is just the same path but in reverse. So rather than going like this, clockwise, you just go counterclockwise. So it's the same path, it's just walked in a different direction. That's why the cost of 1 and 13 is the same. So 1 and 13 both have a total cost of $812 because they're just the same path. It's just one is walked clockwise and the other is walked counterclockwise. Okay, so let's look at where these numbers come from. 185, 121, 174, 199, and 113. So make a note of those and let's go back to the original graph. If you're going to do A, B, C, D, E, A, then you go A to B, it costs you $185. B to C costs you $121. C to D costs you $174. D to E costs $199. And E back to A costs $133. And notice those 5 numbers are what appear here. Therefore, the total cost to the salesman of this trip is $812. So once you've analyzed A, B, C, D, E, A, and its reversal, so just walking in the opposite direction, just move on to the next one. So the next one is A, B, C, E, D, A. So, A, B, C, and remember we just went to D now, but we go A, B, C, E, D, A. That's the route now you want to consider. Well, if you list out all the costs along the paths here, now you get 185, 121, 120 now. So A, B, C, E, right? Going from C to E costs 120. Then from E to D costs 199, and then back to A costs you 152. So that's where those numbers come from. And again, this path in 2 is a mirror image of this path in 14. So A, B, C, E, D, A versus A, D, E, C, B, A. This 14 is just walking backwards. And so on. So what you should do is, when you're given a problem like this, just list all the possible tours with their reversals and just calculate the corresponding cost. If you do that, then you will be guaranteed to find an optimal tour because you've listed everything that could possibly happen. So once you get down to step 11 here, you've found the best one. So once you're finished building this table with 12 rows in it, just scan your eyes down all the costs. 812 is bad, 777 is better, 762 is better, maybe that's it. Oh no, 773, okay, 722 is now a candidate, and then 676 ends up being the best. So the best way to visit these cities is either ADBCEA or backwards AECBDA. It doesn't matter. Okay, so that's what the brute force algorithm does. You literally just list every possible tour, figure out what the costs are, and once you're done, just pick the lowest cost. So pros and cons of this algorithm. The positive aspect of this algorithm is that it is optimal. And what optimal means is that if you implement the algorithm correctly, so in other words, you don't make a mistake in these additions or things like that, but as long as you use the algorithm correctly, you are guaranteed to get the best possible answer. So in the case of the brute force algorithm, we know we are going to get an optimal tour. And we know that because we're looking at all possible tours and just choosing the best one. So the pro of using the brute force algorithm is that it's optimal. It will give you the best answer. And that's what you want, It'll give you the correct answer. Cons, though. The negative aspect of the brute force algorithm is the amount of effort that goes into it. So, look, this graph here is actually really small. So imagine that you are a FedEx driver who's going to make deliveries for the day. You're probably going to stop at, 150 houses, right? Something like that. Way more than 4 houses before returning back to home base, right? Because that's what this graph represents. Start at home base, visit 4 other places, and go home. The typical FedEx driver will visit 100 places in a day, 200 places in a day, I don't know, but way more than 4 houses before returning home. So imagine building a graph with 150 vertices and having to list all possible Hamilton circuits starting at the UPS headquarters or whatever and ending there. There are trillions of them. Just trillions upon trillions of them. As this example had 24, and even that was fairly obnoxious. This table is pretty big, even for a small graph. So imagine having to implement this algorithm for bigger graphs. Okay, it would be just incredibly obnoxious to do. And furthermore, for every single vertex you add just exponentially more obnoxiousness. So going from 5 vertices like this is up to 6 vertices is just really annoying. And then going from 6 to 7 is even exponentially more annoying. So in practice, if this were a classroom setting and I were to now give you a problem, in practice you would only use this algorithm on graphs with 5 vertices or fewer. I never make my students do this on 6 vertices or higher because it just takes way too long. It takes way too long to list all the possible tours, and of course the students are more liable to make a mistake when they're listing these tours. They're liable to write down the same tour twice, things like that. They're liable to miss tours. So anyway, that's a con of this algorithm, and it's a humongous con. It's just so annoying to use this algorithm for a big graph. What does this mean in practical terms? Well, let's start with just human computation. So to solve a traveling salesman problem for a graph with 10 vertices, and again, as real-life problems go, that's tiny. Okay, so 10 vertices means that if one of those vertices is your home base as a delivery person, you're only delivering packages to 9 houses or to 9 businesses or whatever. And, on a typical delivery day, a FedEx guy would deliver way more places than that, right? So the brute force algorithm requires checking 10 minus 1, which is 9, and then 9 factorial Hamilton circuits. That's 362,000 Hamilton circuits, okay? To do this by hand would take, it says 1,000 hours. Who knows how they get that, right? But it would just take a tremendous amount of time. And it's not worth it, right? So even with 10 vertices, which again is really small to model anything real world that actually happens, right? To model most kinds of delivery problems, we're already beyond what humans can do by hand. Okay, so if humans can't do it by hand, what about using a computer? Because computers, of course, can do things way faster than humans. Well, even with technology on our side, it's still really not feasible to use this algorithm using a computer. So your book has a description of what the superhero is. It's basically the fastest supercomputer we have. So imagine that you are a UPS delivery man and you have 19 houses to go to, and then plus your home base to go back to for a total of 20 vertices. Suppose you want a computer to use the brute force algorithm to find you the best route for your day. Well, if you hand the graph, all the distances, to the computer, it will take it 2 minutes to find the best route for you. Okay, 2 minutes is not that long, right? That's not bad. And of course, that's way faster than what you can do, because when you're dealing with 20 vertices, you're talking about checking 19 factorial. Sorry, my phone went off. You're talking about checking 19 factorial routes, and that's just a ton of routes. Okay, there's no way you could do that by hand. Okay, so if you have 19 delivery sites plus home base, the computer can do it really fast. What if you have 29 delivery sites plus home base? What can the computer do then? Well, essentially nothing. Now if you ask the computer, hey, please find me a best route today on my morning route, where I have to visit 29 different houses, you will sit and wait for the computer, for 284 million years before the computer will return an answer to you. Okay, so think about that for a second. The average UPS man will probably make, 40 deliveries in a day, right? So even with 30 deliveries in a day, it will take a computer 284 million years to return an answer to you, okay? So all of this to say, as a summary here, the brute force algorithm is a classic example of what's known as an inefficient algorithm. It's an algorithm for which it gives you the best answer, it gives you a good answer, but you're going to wait around for a long time. And at some point, this table chops off here, but I think once you get to 40 vertices in the graph, which means like 39 delivery sites, you're going to have to wait until the universe dies of heat death before you get an answer. Okay? So even using a computer, this algorithm is just not implementable unless you have a small graph. Small being like, 22 vertices or less. Okay, so that's all I have to say about section 6.3 and the brute force algorithm. The brute force algorithm is a way to solve a traveling salesman problem. And the best thing about it is that it gives you the best tour. The worst thing about it is that, depending on how big the graph is, it's totally unusable. Okay, so it's very simple in theory to just list everything out and see which is the best. But once you start having like trillions upon trillions of tours to list out, it just becomes not practical anymore to use. So in the next two sections, in 6.4 and 6.5, we will turn our attention to algorithms that don't give you the best answer necessarily. Okay, there's no reason to think that they're going to give you the best possible answer. However, they are very easy to implement. So it's not going to take a computer 300 million years to give you an answer with these algorithms. It's just that we won't know that they're giving you the best answer. So we're going to sacrifice optimality for efficiency in the next couple of sections.